Okay, good morning. Today I'm going to talk about a topic known as heat transfer. I'll be quite honest with you, this is it's something I kind of have to cover, and most of it you probably already know. So it's really going to boil down to some definitions and a pretty obvious equation. So I'll go through this relatively quickly. It's probably going to be a half hour, but I'll try to cut down the basics. So we're going to talk about the three methods of energy transfer. And I'm sure you've heard of these before. They're conduction, convection, and radiation. And I will give you a summary at the end, so just hang on and watch, and you'll get what you need to know. So let me start by, this is normally what I do is I do an activity, and because half of us are home, it really won't work that well anyway, but it's kind of a trick question. I hand you two blocks that look identical. One is metal and one is plastic, but they look the same. They have the same shape, but they have some.
Justin Figueroa and Megan Giuliano to the main office, please.
So again, they're two different materials, and I tell kids, okay, put them out on your table, touch them, and the kids feel them, and one feels cold and one feels warm. And so I talk about the hot block and the cold block. And I ask, which one's colder, and the kids figure out, the metal one feels cold and the plastic one feels warm. So then I set this bogus lab where I say, okay, I'm going to give you some ice, and we're going to look at how quickly the hot block melts the ice and how slowly the cold block melts the ice. And you can get some data, and we'll talk about why that happens. So this is all bogus, but everybody thinks it's making sense. So they take out their cell phones, they put the timers on, they put a set amount of ice on each block, and they start recording. And so what happens is that you'll end up with a bunch of ice melting, a big pile of water. These old rings are rubber rings to keep the water from going everywhere. And here's a block of ice that is not melted. I have a video of this occurrence. So this is the company that sells this, called Educational Innovations. They sell the product, and it will probably delay for a while. So let me show you the video of this. And so the cold block is on the left, the metal block's on the left, and it's cold, and the hot block's on the right, and it's plastic. And kids, after about 20 seconds, start looking at me going, wait a minute, what's happening here? The cold block appears to be melting the ice. Well, it's all a big ruse because it wasn't a cold block. This was actually a metal block, and this is a plastic block. And it turns out, the kids think that this guy was the hot one and this guy's the cold one. That makes no sense because the cold block melted. So then they think, oh, maybe I had it backwards. But the whole premise is wrong. These blocks aren't hot or cold. They're actually the exact same temperature. These blocks have been sitting in my closet for 6 months or 12 months since the last time I did this lab. And they are at room temperature. So what's happening here is that the blocks don't have different temperatures. They have different conductivities. So what's happening is when you touch one block, it feels cold, because it's pulling heat out of your body. If you've ever taken rubbing alcohol and put it in your skin feels cold. That's because rubbing alcohol has a very low vaporization point. It's actually taking the heat from your body and it's causing the alcohol to evaporate, which it's extracting heat from your body so it feels cold. This is the same thing. This metal block feels cold because it is taking heat. It can transfer heat very rapidly from one material to another. So it's giving the heat from the block to the ice and melting it. The plastic feels warm because it doesn't pull that heat out very quickly. It doesn't take the heat out of your body, and it also doesn't put heat into the ice very quickly. So it has a very low conductivity. This is a very high conductivity. So again, it's a trick question. The metal isn't hot or cold. It's the same temperature, but it conducts heat more quickly in and out of the material than the plastic does. Now, this is the basis behind the concept known as conduction. So conduction is, this is probably the one you're most familiar with. Conduction is a process where something hot is in contact with something cold, and the heat transfers from the hot side to the cold side. So if I took a chunk of metal and heated it up and took another chunk of metal and had it cold and placed them in contact with each other, slowly the hot would cool down and the cold would warm up, and it would happen until this reached equilibrium. Both sides would arrive at the same temperature. So this occurs because atoms on the hot side are actually literally bumping into and colliding with the molecules of the material in the cold side. And even though they're locked in a crystalline structure, even though they're solids, these atoms vibrate back and forth. So this is vibrating very rapidly. They're bumping into, they're imparting some of that energy into the cold side. So the cold molecules start start moving faster and therefore heating up. And they will likewise transfer that energy from the hot side into the cold side. So that's conduction. And again, I'll give you a formal definition in a second. Now, the classic example of this is the hot iron poker in the fireplace. You hold it with your hand. It's made of metal. It's a very good conductor, but you put the one end into the fire, and as long as you don't leave it in there too long, you're fine. But if you leave it in for a long time, the heat, the high kinetic energy of this fire is going to transfer that heat into the atoms of the iron poker, and the atoms will collide and transfer momentum and energy up the rod, and eventually your hand will burn. But most people don't hold it that long. If you cook, you are familiar with this concept. I actually like cooking. I cook at my house, and I will heat a pan. I cook swordfish in a pan. I'll sear it. Then I'll take the entire pan and throw it in the oven and leave it in it for 15-20 minutes. Well, I take a pad, oven mitt, and I'll pull it out so I don't burn my hand. But then I forget this is actually hot, and I grab it in my hand. So it's 400 degrees, and I grab my hand. I always burn my hand. So they make things for people stupid like me. They make wooden handles that protect your hand. So the metal is a good conductor. It transfers the heat from the metal into my body, which I don't like. But the wood is a very good insulator. It's the opposite of a conductor. So this is a very poor conductor, very good insulator. It keeps the heat from transferring. That's what we're really going to talk about, is different types of transfer. Now, we usually, in physics, we talk about the conductivity versus the insulating. So these are opposites of each other. Different materials conduct heat at different rates. Some things are really good conductors. They have a high K value or conductivity rate. And if they have a low K value, they're called insulators. So these are opposites. And again, the AP almost always talks about conductivity versus insulating. They typically give you a lab setup. I'll talk about a lab in a minute, but they have something that's hot on one side, it's cold on the other side. So there's a big temperature gradient, big temperature difference, and they have some material, a certain thickness in a certain area. So you think about your house, for example, it's maybe cold outside and it's hot inside. You want to keep that hot inside. You don't want the heat going out. And so we have a certain thickness in a certain area to keep that from happening. We used to do a lab in class. I'll show you a lab. Essentially the lab we did in class was exactly the lab in 2019 for the AP, and we basically look at how different materials conduct heat through that material. I'll get to that lab in a second. This is something I'd love to do. They won't let me do it because it probably hurts children. But here, this is a rod that's made up of 5 or 6 different metals. So each of these metals has a different conductivity rate. And I, of course, would be holding the non-conducting plastic handle, but I had each of my students hold with their bare hand, they'd hold the metal rods, and then I take a blowtorch and heat the center here. And based on these different materials, the energy will conduct through these as the rapidly moving molecules bump into other molecules. They'll transfer the energy. Now, of course, I'm safe because I'm holding plastic to the insulator, but kids would hold on until they can hold on anymore. I apparently asked to do that, and they said, no, you're not allowed to do that. I thought it'd be fun. Now, different values. Again, the K value is the conductivity value, and as you might suspect, metals have really good conductivity values. They have high numbers. Aluminum's a very good conductor. Copper is an excellent conductor. Terrific conductor. In fact, this is why pans, if you probably have a set of pans at home that either have a aluminum bottom or a copper bottom, and that's because we want to transfer the heat from the fire into the food very quickly. So you cook with this material. Sometimes you don't want things that conduct, you want them to insulate. So sleeping bags are mostly made up of air because air has a very low energy per unit time transfer rate. So air is actually a really good insulator. Water is also a very good insulator. So Long Island Sound, you may live in Monroe, but down in Long Island Sound, this water holds on. It takes a long time to heat up this in the springtime. This water is very cold for a long time, even though the land may be warm. But right now, this water has been heating all summer, and it's holding on to that heat. So it may be 50 degrees in Monroe, but it's 60 in the fall down by Bridgeport. So again, this water takes a long time to heat up, and it takes a long time to cool down. So boiling water takes a long time. But if you check that pan an hour later, the water is still hot, even if you take it off the stove. So some things are good conductors or good insulators or poor conductors. Now again, this is typically what the AP asks. They give you to say, okay, here we got some material of a certain area, has a cross-sectional area at the end, it has a certain thickness, and if you put a temperature gradient or temperature difference, hot side, cold side, how quickly does that energy flow across that? And as you might suspect, how quickly it flows depends upon the thickness, the area, how hot and cold it is, and what it's made out of. So there's an equation. This is and I'm not sure you really got to know this. Maybe a good idea to stop the video and write it down, but this is the energy per unit times, how quickly the energy flow rate of that energy through that material depends upon the conductivity of that material, the area of that material, and how the temperature difference on either side. This is really delta T. That's how hot it is on one side and how cold it is on the other. If the temperature difference is only 1 degree, it's not much. But if it's 1,000 degrees on one side and 0 on the other, it's going to conduct much faster. And then, so the conductivity, area, and the temperature difference affect how quickly it goes. Each of these is directly proportional to the rate. But if it's a large area, if it has to travel through a great distance, that will slow it down. So it's inversely proportional to the distance. And again, that's kind of a common sense equation if you think about it. Now, this was the this was the actual AP Physics 2 question from the 2019 test. Actually graded this one in Kansas City. It's horrible. It's basically the lab I was talking about a minute ago. You have a hot plate, and on the hot plate you put a slab of plastic, something that's going to either conduct or insulate, and then you put some ice in a little dish. And then you have a little spout that, as the ice melts, it will collect the water. And so this hot plate will boil the water, energy will conduct across the slab of plastic, and it will melt the ice. And they change the thickness of the plastic, and as you might suspect, the thicker it is, the slower it conducts. So basically just asking you to make a graph and get some data and confirm the equation we just talked about. So it's kind of common sense. If this is hot and this is cold and this is thick, you're going to affect the rate at which the energy transfers over. We can collect water to see how quickly that ice melted. Again, I won't worry about that particular question, but the concept's an important concept. Now, you do not need to know this. This is R values. This is the opposite. If you own a home, you care about R values, because R values are what determine the insulation in your house. So here's a typical picture in New England where you see a house and you can actually see the snow on the roof, but you also see the rafters in the roof. And is that good or bad? Well, if I'm paying the heating bill, that's bad, because heat from inside my house is passing through that material. So it's hot inside, cold outside. Heat's coming out, and it's causing this snow to melt. I don't want to melt snow.
Michael Katz, please come to the main office. Michael Katz to the main office.
I don't want to melt snow. I want to keep my house warm. So any energy that's going into the roof is wasted energy. So people do care about this, and you probably live in a house where somebody else pays the heating bill, but when you own your own house, you're going to care about this. So different materials have different R values or insulating values. You do not need to know this. I covered this for UConn one year. UConn had a question related to this. So in my house, I try to have lots of insulation to keep the air conditioning in or to keep the cold out. So whether you're in the north or in the south, that's what matters. So and different materials have there's building codes in every part of the country to make sure you're not wasting energy, which is a good thing. We don't want to waste energy. So, and most people have this pink insulation in your house, and the thicker the layer of insulation, the better the R value, or the better the insulation value. Now, there's a really cool demo. I used to do this in class, but it created a ton of smoke. It's a conduction demo, and again, I know I haven't defined conduction yet, really, but what I do is I take eggs, scramble up some eggs, and pour them into a paper bag. So I take 3 eggs, crack them, put them into a dish, scramble them up, pour it into a paper bag, and then set the paper bag onto a hot plate or onto a fire. And it turns out the plates of the bag will not catch on fire. It's a weird concept. Now the Boy Scouts did a video of this. Put this down. But basically, you take a paper bag, you take some bacon, you take a knife, and take some eggs. You cut up the bacon. You have a campfire. You actually can use flame. They say don't use flame, but you put the material into the bag, crack the eggs right into the bag, set it right on the fire. Now they're going to hold it above, but you can put it right on the fire. The bag will not catch fire. The bag will not catch fire. So what happens is that the energy travels up into the bag. The energy actually travels up into the bag, and all the heat goes into cooking the eggs. The paper acts as a conductor, and the eggs absorb the energy. So the heat that's trying to burn the paper is actually going in to cook the eggs. So as long as the eggs aren't cooked or vaporized away, the paper bag will not catch on fire. Now, I do this in class, but there's so much smoke. The whole room fills full of smoke. So it's kind of cool, but it's not great to do in class. So the video is better. And you can try this at home someplace, carefully. So this is conduction. So this is the thing, you might want to stop the video and write down the definition, but it's basically heat is transferred by means of molecular agitation or collisions. So down at this end we have heat being applied to, say, a piece of metal. The heat causes the molecules to move back and forth rapidly. The high energy particles will collide with the slower moving molecules to their side, and then these will then therefore move faster, and this process continues down. If you hold your hand long enough here, it's a good conductor, your hand's going to get hot. So, just grab an iron poker and put it in the stove for a couple hours and just wait, and your hand will catch on fire. So that's the basic idea behind conduction. You need to have a collision between molecules to transfer the kinetic energy. Now, we used to do a lab in Yukon physics on calorimetry. You probably did this in your chem class. You heat up some metal, then drop the metal into a cup of water, and you saw the water heat up. So the basic idea is that the hot metal lost energy and the water gained energy, and you can calculate the conductivity of the metal that way. Certain metals conduct really well, and some others aren't so good. So we don't need to know that for physics. Now, the second process is known as convection, and I'll go through this relatively quickly. Convection means mass movement. So a classic example of this is clouds in Florida. If you go to Florida in the morning time, it's sunny out, the heat from the sun comes down, heats the ground. We'll talk about that in a minute. The air near the ground gets warm, and that air, therefore, its density changes because the molecules start moving faster, they spread out, the density goes down, and so the hot air starts rising. Now, as it rises, it actually cools down. We'll talk about that later as well, but the idea is hot on the bottom, the air molecules get hot, and the air itself is actually moving. So the air molecule down on the surface, actually literally the same air molecule, moves up along with all its friends. So you actually have wind being generated, and it actually causes hot to rise and cold to sink. That process of mass movement, where all these molecules are moving freely, unlike collisions with conduction, we have convections of mass movement. Now, a good example of convection is actually a radiator, and the name radiator is horrible. It should be called a convectionator. So if you think about it, most of you probably have this around your house. You probably have baseboard heat. You might have a vent in your floor that blows hot air in, but they put it in the floor because the hot air is going to come in, it's going to rise to the top. So you don't put the radiator or the convectionators on the floor, on the ceiling, you put them on the floor because we want that hot, there's a pipe running through here that carries hot water. That hot water, by conduction, actually heats the air, but then the air gets warm and the air actually rises. So you actually have conduction to heat the air, and then the air itself rises, and that creates convection. So the hot air goes up, cold air gets pushed down, that cold air gets heated by these pipes again and goes up. So you actually have convection inside the rooms of your house. I grew up in an old farmhouse with my parents, and they had this type of radiator. Same thing, hot water runs in, heats the metal radiator or convectionator, the air gets warm, the air rises, and you get this convection cycle. Same thing happens when you boil water. The flame goes by conduction, goes through the pan, heats the water. The hot water is less dense, so it rises, and the cold water sinks. So these are called convection cycles. Same thing happens inside the Earth with plate tectonics. You have hot magma inside the Earth that rises up, drives the plates, the continental plates, and makes the continents move. So this process of convection is very important. You may have a convection oven. It's basically the same thing. They heat the air rises. Sometimes they put a fan in there. Really, convection ovens is an oven with a fan. It drives the air back down. So you get these convection cycles. It's good for cooking things like cookies, so they come out even. You don't have burnt cookies on one side. So the second process was convection. The third process is radiation. This one's definitely strange. Mr. Horgan probably talked about this a little bit last year in Physics 1 when we talked about waves. Remember, you guys took a look at mechanical waves, which were transverse or longitudinal, like sound. And for waves in Physics 1, you had to have something waving. Something was waving. So in sound, the air is waving. When you drop a rock in the pond, the water is waving. But you may recall he also talked about electromagnetic waves, where nothing's waving. There's no medium. You don't need anything to be waving. There's no physical thing waving. So Electromagnetic waves, and we'll certainly study this a little bit later, we have electric fields and we have magnetic fields, and what's actually waving is not a medium, it's actually a fields. You can't see a field, you don't feel, you can see the effects of a field. So it's a very abstract concept. So the classic example of this is the sun. The sun sends out electromagnetic waves. And it has to be that way because the sun is not in contact with you. You don't feel the heat from the sun because it's conduction. You'd be toast. So it's not conduction. It's also not convection. The sun doesn't heat air and send the air through empty space. So there's nothing touching you and there's nothing being sent by the sun to the earth other than these electromagnetic waves. And these waves travel through empty space. They interact with the cells in your body, and they cause those cells in your body to, the electrons in your body to oscillate up and down, and you feel it as heat. And it's kind of like if I throw a rock in the pond, the wave travels across the pond and causes the rubber ducky on the pond to bob up and down. Well, the same thing's happening with the sun, but it's sending out waves through empty space that aren't physical waves, or nothing material is waving. So we classify them as electromagnetic. Now, we classify the electromagnetic spectrum based on different types of energy. And the basic idea is we call them electromagnetic spectrum, and it includes light. But there's radio waves, microwaves, infrared, ultraviolet, visible light, X-rays, and gamma rays. And it's really classified based on wavelength or frequency. It's kind of what the periodic table is to the elements. The periodic table organizes the elements by their atomic number or number of protons. The electromagnetic spectrum organizes electromagnetic energy based on its wavelength or its frequency. The wavelength, you recall, is how far from crest to crest. We can say this has a long wavelength compared to these, or you can say it has a low frequency. This would be a high frequency. So it depends how they classify it. But generally, radio waves, the sun sends out all of these things. The sun sends out radio, TV waves, and microwaves, infrared and ultraviolet and visible light, X-ray and gamma. Now luckily, these things are pretty dangerous. When you get down to this high frequency, low wavelength, these interact with the cells in your body and cause bad things to happen. The good news is that the Earth's outer atmosphere and the magnetic field protect us against some of this stuff, whereas this stuff can travel through. So we get light and we get heat. Infrared is translated as heat. Your body in this wavelength is heat energy. So we see light and we see heat from the sun. We also can detect these things, and we luckily don't have to worry about these things in the sun. So these are electromagnetic waves that travel and carry energy. So the sun's sending us energy. It's an energy transfer. I'm not going to go into this in great detail. I really want to speed through this quickly. It's already too long. But again, the basic summary of this is conduction, convection, radiation. Conduction requires collisions between high energy and low energy particles to transfer that energy from the hot side to the cold side, poker in the fire. Convection is mass movement. It's usually air or liquid. And again, the medium actually literally moves. So the air moves from one location to another, or water moves from one location to the other. And a good example of that is hot air rising. And finally, radiation is energy is carried by electromagnetic waves. There's no medium required, although there could be a medium. And higher frequencies carry higher energy. And so light and heat from the sun travels to the earth. So that's a real quick summary of the three methods of heat transfer. There's usually a multiple choice or two. Some years there are questions that there are problems, but they're not usually calculations. They're usually explanations of what's happening. So I'm pretty comfortable that this would be enough for you to know the basic idea. And I usually cover this as a video because sometimes it can drag up to a couple of days and it really doesn't need to be other than that demo at the very start. So that's all for today for that content. Thank you very much.